The content in this presentation is covered on pages 99 through 109 of your textbook, and it's meant to help you achieve learning objective number 21, which is to list and describe the ways relative humidity changes in nature and to compare relative humidity to dew point temperature. So be sure to read these pages before watching the video and to read them a little bit more carefully before attempting the online quizzes. The dew point temperature, or simply the dew point, is that temperature at which water vapor begins to condense. The term dew point stems from the fact that during nighttime hours, objects near the ground often cool below this temperature and become coated with dew. So you've seen dew or condensation form on cold drinks on a hot summer day in humid environments. In nature, cooling air below its dew point temperature typically generates dew, fog, or clouds when the dew point is above freezing, and frost when it's below freezing. Dew point can also be defined as the temperature at which air reaches saturation and is therefore directly related to the actual moisture content of a parcel of air. The most familiar and unfortunately the most misunderstood term used to describe the moisture content of air is the relative humidity. So we'll say it again and show it to you a couple times, but make sure to jot this down. Relative humidity is a ratio of the air's actual water vapor content in the upstairs number, the upstairs part of the ratio, and compared with the amount of water vapor required for saturation at that temperature. So it's a little confusing, but I'll say it again. The relative humidity is the ratio of air's actual water vapor compared with the amount required for saturation. So it's the amount of moisture that the air contains in the numerator, the upstairs number, and the maximum amount that it can contain in the denominator, the bottom. So relative humidity indicates how close to being saturated the air actually is, not the actual quantity of water vapor in the air. So I know this is yet another term about atmospheric moisture, and it's starting to be a little confusing. But let's keep these definitions, the different definitions, in one separate place of the notebook, and then we can come back to this section of the notes and compare the definitions before we start studying for the test. Okay, students frequently have trouble the first couple of times they do it calculating or determining the relative humidity. And I think the reason is that there's a lot of language, a lot of different terms that have similar names. So I want to just show you quickly that what we're talking about is the relative humidity of the air. It has its own equation, right? We said in the last slide that it was the mixing ratio of which is the amount of water vapor in the air, divided by the saturation mixing ratio. So what is the current mixing ratio of the air, and how much water will be present once it's saturated? So remember, the mixing ratio is this equation up in the top right corner. It's the amount of water vapor, the mass of water vapor in the balloon of dry air, an imaginary balloon. So under non-saturated conditions. So we still have more vapor that we can add to this before saturation occurs. We'll have a lower mixing ratio than its saturation. And so once we get to the saturation mixing ratio, well, that's as much air, that's as high as the mixing ratio can go. So looking at a table like the one we used in the thought experiment in the last video, you can see that at 25 degrees centigrade, air is saturated when it contains 20 grams of water vapor per kilogram of air. Okay, so that would be its saturation mixing ratio. So if the air contains only 10 grams per kilogram, right, that's the mixing ratio, on a 25-degree day, the relative humidity would be 10 over 20. Right? How much we have is 10. The saturation that we determined in the lab, saturation mixing ratio, is 20. So we have what? A 50% relative humidity. If we then took that 25-degree air and added moisture to it, another 10 grams per kilogram, the relative humidity would be 20 over 20. And then we would have 100% saturation. So remember, that's just how much water could the atmosphere hold? 20, right? It's not, relative humidity of 100% does not mean, and it can't possibly mean, that the air around us is completely water, right? It just means that it's holding as much water as it possibly can before a cloud forms. Because relative humidity is based on the air's water vapor content, as well as the amount of moisture required for saturation, it can change in one of two ways. First, relative humidity changes when water vapor is added to or removed from the atmosphere. Notice that in this figure, it's another thought experiment. What we're doing is keeping the temperature constant. So you see the thermometer in each of these three pictures stays at 25 degrees C. Also, the flask that's sitting there on our imaginary lab bench is a closed system. So we add water vapor to the air just by letting the liquid water evaporate. Under these conditions, the relative humidity of the air increases until saturation occurs. That is, until we reach 100% relative humidity. If you actually set this experiment up in a real laboratory, you would notice that the liquid level of the water surface would fall, just like they're showing you in that picture. And eventually, you would see drops of water forming on the walls of the flask when the air becomes saturated. But what if even more moisture is added to the air parcel? Does the relative humidity ever exceed 100%? Not under most circumstances, no. That situation doesn't really happen. Instead, the excess water condenses. So we get to 100% saturation, and then any other water in the air condenses to form the liquid water. So you've seen this happen when you take a hot shower. The energy in those water molecules is very high. It's very excited. That means that the rate of evaporation is high. It's easy to get those molecules vibrating fast enough to where they convert to the point where they convert to vapor. So as long as you run the shower, the process of evaporation continually adds water vapor to the unsaturated air in the bathroom. If you stay in that shower long enough, the air eventually becomes saturated and the excess water vapor begins to condense on the mirror, the window, the tiles, the towels, and any other surface in the room. In nature, moisture is added to the air mainly through evaporation from the oceans, but plants transpire. They add vapor to the atmosphere, and soil, every little soil particle, there's evaporation going on around the edges of the soil. Small bodies of water. I look outside where I am in North Bend, and the river that's running by the end of our housing development, the middle fork of the Snoqualmie, makes clouds on a daily basis. A lot of evaporation occurs all over the place in nature. So unlike in the shower situation, the natural processes that add water vapor to the air generally don't operate at rates fast enough to cause direct saturation. One exception, and there are other exceptions, is when you exhale on a cold winter day and you can see your breath. That warm, moist air coming from your lungs mixes with the cold air around you. Your breath has enough moisture to saturate a very small quantity of cold outside air, and that makes a miniature cloud. Almost as fast as the cloud forms, though, it mixes with the surrounding dry air and evaporates. The second way to change relative humidity is to change the temperature, because the amount of moisture required for saturation is a function of air temperature. So remember that warm air holds more moisture? Well, look at this set of flasks on the imaginary lab table and notice that when the air at 20 degrees C contains 7 grams of water vapor per kilogram, it has a relative humidity of 50%. If you were to cool that flask from 20 to 10 degrees C, as you see in the middle picture, the relative humidity increases from 50 to 100%. So we could conclude that when the water vapor content remains constant, a decrease in temperature results in an increase in relative humidity. But there's no reason to assume that cooling would cease the moment the air reached saturation. So what happens when the air is cooled below the temperature at which saturation occurs? We'll look at the difference in the liquid water between the middle flask and the one on the right. When the flask is cooled to 0 degrees C, the air is saturated at 3.5 grams of water vapor per kilogram of air. Because this flask originally contained 7 grams of water vapor, 3.5 grams of water vapor will condense to form liquid droplets that collect on the walls of the container. In the meantime, the relative humidity of the air inside remains at 100%. So this brings up an important point. When air aloft is cooled below its saturation level, some of the water condenses to form clouds. Since those clouds are made of liquid droplets or ice crystals, the moisture is no longer part of the water vapor content of the air. Conversely, an increase in temperature results in a decrease in relative humidity. For example, assume that the flask on the left, containing 7 grams of water vapor, is heated from 20 degrees to 35 degrees C. The table from our experiment in the last presentation indicates that at 35 degrees C, saturation occurs at 35 grams of water vapor per kilogram of air. So by heating the air from 20 to 35, the relative humidity would drop from 7/14, 50%, to 7/35, 20%. In nature, there are three major ways that air temperature changes. So we can see the way that air temperature change influences or brings about a change in relative humidity can really happen in three important ways. Maybe some other ones, but these are the ones that happen over relatively short time spans so that we would see a change in the weather. The first of these ways is that we have a daily change in temperature. So if we think to those lab experiments that we were imagining, and we see a daily change in temperature, as shown by the thermogram on the top left here in this slide, we know that we have a daily low temperature that occurs at about 6 a.m. And then throughout the course of the day, because of the incoming radiation, we expect to see that temperature climb until we reach a maximum, a daily temperature max, at around 6 p.m. So if we're raising the temperature in our container all day long, what would you expect would happen to the relative humidity? Just like in that last thought experiment, it would decrease, and we actually see that happen. So on a daily basis, if we're not seeing the input from a big frontal weather system or something like that, we will see the highest relative humidity in the morning and the lowest one in the late afternoon. So another way that we can affect relative humidity by changing the temperature is when we do see a frontal system come in. So temperature changes happen that result whenever we see a big cold air parcel move in, right? We lower the temperature automatically, and what happens to the relative humidity? It'll increase. And the third way is when we see a vertical change, right? So we'll see a big bunch of convective cooling going on. So a warm air parcel caused by solar radiation bombarding the molecules on the ground causes the ground temperature to heat up, and we see a big bubble of air rise up through the atmosphere. That's an example of a vertical motion. Okay, so we can think of a daily cycle, frontal weather, or thermal air, so rising warm air. The effect of these three processes is shown in the figure here. So during the mid-afternoon, relative humidity reaches its lowest level, that air, the mixing ratio, the actual water vapor content remains unchanged. Only the relative humidity varies. So we'll consider all of these processes in more detail in later presentations. But to summarize, relative humidity indicates how near the air is to being saturated, whereas the air's mixing ratio is what tells you the actual quantity of water vapor contained in the air. So when the water vapor content remains constant, relative humidity drops with an increase in air temperature, and conversely rises with a decrease in air temperature. On the weather map, recall that the saturation vapor pressure is temperature dependent. So that means for every 10 degree C increase in temperature, the amount of water vapor needed to saturate the air would double. Therefore, cold saturated air contains about half the water vapor of saturated air that has a temperature of 10 degrees C, and roughly a quarter of the saturated air with a temperature of 20 degrees C. Because the dew point is the temperature at which saturation occurs, we can conclude that high dew point temperatures equate to moist air, and conversely that low dew point temperatures indicate dry air. And to be more precise, based on what we've learned about vapor pressure and saturation, you could say that for every 10 degrees C increase in the dew point temperature, air contains about twice as much water vapor. So they're related in a nonlinear fashion. So you know that when the dew point temperature is 25 degrees C, air contains about twice the water vapor as when the dew point is 15 degrees C, and 4 times that of an air with a dew point of 5 degrees C. And because that dew point temperature is a good measure of the amount of water vapor in the air, it commonly appears on weather maps, even though a lot of people don't really know what it means. When the dew point exceeds 65 degrees Fahrenheit, or about 18 C, most people would consider that to be really humid air. With a dew point of 75, the humidity is oppressive. Notice on the map here that much of the southeastern United States has dew points, temperatures that exceed 65. Also notice that although the southeast is dominated by humid conditions, most of the remainder of the country is experiencing relatively dry air. So some of this is related to the temperature patterns that we saw in last week's presentations. We can see that the Mid-Atlantic, for example, a big purple part of the map, right? So 70 plus, and so we really do have that pea soup humidity. We don't see that in the Pacific Northwest. We see much more comfortable humidity. That's a result of the different air parcels that we see, the mixing of those air parcels, where you see the minimum values are the high elevations in the American West, and mostly that's because we have a very arid region there. We don't get much rain. There isn't much moisture to be had. Quickly, I want to just review for you guys in this presentation how you measure relative humidity. It's an interesting thing. I haven't located any sling psychrometers in our lab prep room, but I'll try to do so. We'll get a chance to actually go and measure these. A sling psychrometer is really nothing more than 2 identical thermometers mounted side by side. One of them is called the dry bulb, and that measures the air temperature. The other one is called the wet bulb, and it has a little wick on it, a thin piece of cloth or gauze affixed to the bottom. So what you do is you saturate the cloth wick with water, and you generate a continuous current around that wick, either by spinning the psychrometer, it's on a little hinge, or by using an electric fan to move the air past the instrument. So as a result, water evaporates from the wick, absorbing heat energy from the wet bulb thermometer that causes its temperature to drop. The amount of cooling that takes place is directly proportional to the dryness of the air, how much that the air's ability to soak that moisture out. So the drier the air, the greater the cooling, and therefore the larger the difference between the wet and dry bulb temperatures. So if you have a big difference between the two thermometers, you have a relatively low humidity. By contrast, if the air is saturated, perfectly saturated, you won't see any evaporation occur from the wet bulb, and the two thermometers will have an identical reading. So using a psychrometer and some special tables, which we'll use in laboratory, you can determine the relative humidity and the dew point temperature just by kind of looking them up on these tables. There are a number of different hygrometers, which are similar inventions, but this is the most commonly used one. We'll talk about other mechanisms in a different, maybe in class. So use the content provided on the Canvas site as well as any outside sources to verify that you can formulate the answers to these questions. And I know there are a lot of them in this. This is kind of a long presentation. If you can comfortably answer most of these at least, you're in great shape. If you can't, let's talk about it. Rewatch the textbook, reread the textbook, I should say. Don't watch your textbook. Watch the videos, reread the textbook, and if you're still stumped, come and talk to me.